Good morning, students. Dear students, today, in continuation with the lectures on motion on a straight line, we will discuss part 11. Part 11 of the video lecture, and in this, we will discuss about the kinematic equations for uniformly accelerated motion. Equations for uniformly accelerated equations for uniformly accelerated motion, and in this we will discuss about the velocity time relationship, position time relationship, and position velocity relationship. First we discuss about velocity time relationship. Velocity time relationship. Velocity time relationship. First we will draw the graph. Here we are taken velocity. Look at here, students. This is the initial velocity u, and this is the final velocity v. This is the final velocity v. The initial velocity u is at time t is equal to 0, and the final velocity is time t is equal to t. This is time axis, this is velocity axis. Now we have joined it and we had marked it as P, Q, R, T, O. P, R, T, O. Now we have to find the velocity time relationship, and we know that acceleration is equal to slope of velocity time graph. Acceleration is equal to slope of velocity time graph, and the slope of velocity time graph can be given by this angle theta. So acceleration is equal to tan of angle theta. This tan theta gives the slope of velocity time graph, and so tan theta is equal to QR upon PR. QR upon PR. On the velocity axis at point Q there is velocity v, and at point R the velocity is u. So QR is equal to what? QR is equal to v minus u. So you can get it as QR is equal to v minus u, and PR, that is OT, and it is equal to t. So you can write it as A is equal to v minus u upon t, and you can write it as v minus u is equal to at, or is v is equal to u plus at. V is equal to u plus at. This is the velocity time relationship. This is velocity time relationship. Now from the same graph we will discuss about position time relationship. Second one is position time relation. Position time relationship. For position time relationship the area under Wittig graph. The position or displacement can be given as the area under velocity time graph. Area under velocity time graph. It gives us position. So how can you find the area under velocity time graph? Means the area of triangle PQR plus the area of rectangle PRTO or PORTR. So area under VT graph can be given as area of triangle, right angle triangle PQR plus area of rectangle PRTO, area of rectangle PRTO. So area of triangle half base into height, half into PR into QR, base into height, plus area of rectangle PRTO is equal to length into breadth, OT into RT. So you can write it as half PR. PR is equal to T and QR is equal to V minus U, plus OT, that is T, and RT, that is U. So X is equal to UT plus V minus U. From first equation you had discussed that V minus U is equal to AT. From equation first, V is equal to U plus AT, or V minus U is equal to AT. So you can replace V minus U as AT. So half into T into AT, or X is equal to UT plus half AT square. S is equal to UT plus half AT square. This is the position time relationship. Now the next one is position velocity relationship. The third one is position velocity relationship. Position velocity relation. Position velocity relationship. In position velocity relationship, you have to find the area of this trapezium. For position velocity relationship, we have to find the area of trapezium. So displacement in time interval T is given by displacement in time interval T is given by X is equal to area of trapezium, OPQT, area of trapezium OPQT, and it is equal to half OP plus Q2 into the separation, that is equal to OT, that is equal to half OP is what? OP is U plus QT is V into T. Now look at here. From first equation you know that V minus U is equal to AT, or from here you can calculate that A is equal to V minus U upon T. Putting the values here, X is equal to T is equal to V minus U upon A. So X is equal to 1 by 2 U plus V into V minus U upon A, and you can write it as X is equal to V square minus U square upon 2A, or you can write it as V square minus U square is equal to 2A. This is the velocity, position velocity relationship. So these are the three relationships. From the graphical method we had calculated the three relationship. Now we will discuss about displacement of the particle in nth second. Displacement of particle in nth second. Displacement of particle in nth second. What is the meaning of displacement of the particle in nth second? Let us understand. In first second, suppose the particle had traveled 1 meter. In second, 2 meter. In third second, 3 meter. In fourth second, 4 meter. Up to so n minus 1th second, n minus 1 meter. And nth second, n meter. So if it is said to you to find the displacement of the particle in fourth second, means fourth second, so what you have to do? Displacement in fourth second minus displacement in third second. In between, suppose it is asked that from first second to second second how much the particle had displaced in between these 2 seconds. So from displacement in second second minus displacement in first second, you will get the displacement in between these 2 seconds. Similarly in this between these 2 seconds. So if you have to find out the displacement of the particle in nth second, so displacement of the particle in nth second minus 1th second, you will get how the particle displaced in these 2 seconds. So similarly we will find the displacement of the particle in nth second. Displacement of the particle in nth second. So displacement of the particle in nth second, Sn minus 1. So it can be written as Snth. So Snth is equal to Un plus half An square minus Un minus 1 plus half a n minus 1 square, or un plus half a n square minus un plus u minus half a n minus 1 square, or u plus a by 2 n square minus n minus 1 whole square. And on solving here, u plus a by 2 n square minus n square minus 1 plus 2. It will be cancelled out, and you can write it as nf is equal to u plus a by 2 2n minus 1. This is the expression for the displacement of the particle in nth second. Suppose it is given the question that initial velocity of the body is 6 meter per second and its acceleration is 3 meter per second square, then find the displacement of the particle in 6th second. So you have to put the values n is equal to 6, and directly by putting n is equal to 6 you can get the answer, the displacement of the particle in 6th second, or similarly 12th second, 10th second, 9th second you can easily calculate. So this is about the displacement of particle in nth second. Now we will calculate the equation of motion by calculus method. Equation of motion by calculus method. Equation of motion by calculus method means we use the concept of differentiation and integration here. Means the mathematical operators, that is integration and differentiation, we will use here to find the equation of motion. So first, that is velocity time relation. Velocity time relation. As we know that acceleration a is equal to dv upon dt. Acceleration a is equal to dv upon dt, and from here we can find that dv is equal to a into dt. dv is equal to a into dt. Integrating both sides. Integrating both sides. On doing integration both sides, dv and here a dt. This is the sign of integration, and at t is equal to 0, the velocity is u, and at t is equal to t, the velocity is v. So you can write here as dv. So integration of dv is v uv, and a is constant, t 0 to t, and you can write it here as upper limit minus lower limit, that is v minus u is equal to a into t, or you can write v is equal to u plus at. V is equal to u plus at. This is the velocity time relationship by the help of calculus method. Now, position time relationship. Position time relationship. Second one is position time relation. So position time relationship, and in position time relationship we relate the velocity with position, that is dx upon dt, and from here we can write it as dx is equal to v dt. Dx is equal to v dt. Now dx is equal to v dt. Integrating both sides, dx and v dt, dx and v dt. At t is equal to 0, position is x naught, and at t is equal to t, position is x. Now you know that u plus at into v is equal to u plus at, or v minus u is equal to at. So you can write it here as dx x naught x u dt 0 to t plus 0 to t at dt. Now look at here, x dx, integration of dx is equal to x, and x naught into x, the initial velocity remains constant, and it will be taken out u. Integration of dt is t, and it is equal to 0 to t plus uniform acceleration, so a will be taken out, and it is equal to t square upon 2, 0 to t. It is equal to x minus x naught ut plus half at square, upper limit minus lower limit, and you will get the position time s is equal to ut plus half at square. S is equal to ut plus half at square. Now the last one is position velocity relationship. Position velocity relationship. Position velocity relation position velocity relationship. For position velocity relationship, we have to take a acceleration a is equal to dv upon dt, and dv upon dt can be written as dv upon dx into dx upon dt, or you can write it as a is equal to dx upon dt is equal to v into dv upon dx, and from here you can write it as a dx is equal to v into dv. A dx is equal to v. I am integrating both sides. Integrating both sides. U v v dv is equal to a dx. Initial position x naught and final position x. And from here you can write that integration v square upon 2 uv, and a is the constant acceleration, so a we can outside x naught x, and from here you can write it as v square minus u square upon 2 is equal to a upper limit minus lower limit, that is x minus x naught, and v square minus u square is equal to 2a x minus x naught. That is, this is the position velocity relationship, that is v square minus u square is equal to 2as x minus x naught can be taken as displacement, so v square minus u square is equal to 2as. This is all about the position time relationship, position velocity relationship. So this is all about today's video, students, and in the next video we will discuss the concept of relative velocity and do certain numericals based on these. Thank you, students. Have a nice day. Take care.